JPL is at the forefront of climate science research. Today, NASA has 16 space missions and numerous airborne missions collecting climate data. We're going to learn about all of it. Some of what the scientists at JPL are doing right now includes leading the effort in documenting the loss of ice from the world's ice sheets, leading the world in monitoring sea level rise, pioneering the use of satellite observations to study the circulation and mixing that occurs in the world's oceans, pioneering the way CO2 is observed globally, observing critical aspects of Earth's water cycle from space, leading the effort in monitoring key atmospheric gases important for understanding the effects of climate change. And we're going to learn all about these today, and there will be a test at the end, so take notes.
What I do is I study global warming and the rising oceans, essentially. One of the most important and biggest indicators we have that humans are changing the climate is the rising oceans. So if we look at the planet from space, remember that 2/3 of the planet is covered by oceans. So if you're really wondering where is global warming happening, 2/3 of the Earth is covered by oceans. Really, it's happening in the oceans. It turns out that over 90% of the heat trapped by greenhouse gases is going into the oceans. So that heat is warming up the oceans, it's causing them to expand, and that's one of the things that causes sea level rise. Of course, the seas are also rising because the icebergs and ice sheets and glaciers all around the world are melting. And as that water melts, it runs off the land into the oceans, and it causes sea levels to rise as well. So in a way, sea level rise is kind of a double whammy in terms of measuring climate change. It tells us how much heat is going into the ocean and also how much glaciers and ice sheets are melting. So it's, in a way, the most important indicator we have that humans are changing today's world in a very dramatic way.
If you put this all together about what's happening, what we do as human beings is a number. I'm not going to talk about the units today, don't really need to, but that number over there is the sum of all our activities. We're putting about 10 now, not just 8.5, it's closer to 11 actually, gigatons of carbon into the atmosphere every year. The growing economies in China, India, are just moving that ahead enormously and rapidly.
So there's not very much information that we have about the Arctic. And yet, all of the models that Mike was telling you about before and all of the measurement data that we have in place suggest that the Arctic has been warming at about twice the average global rate over the last 50 or 100 years. So it's actually accelerated warming compared to what you're experiencing everywhere else. Additionally, because it's so brutal up there, the ecosystems and the climate system itself that has evolved is very, very, very highly evolved for that brutal environment where you have maybe 80 or 90 days of thaw during the year, and the other 270 days are frozen. Okay? And so this is a very, very sensitive part of the climate system, very sensitive animals, plants, ecosystems, and anything that's going to happen in terms of change there, you're going to be more likely to be sensitive to that in the Arctic than you would anywhere else in the world.
Volume and a lot of space on board the spacecraft. Now, if that's all this tool could do, that would be kind of not so fun, but what it's really for is the data these missions are collecting that goes from the very, very simple, perhaps a little bit more abstract and hard to understand. This is the simple end. This is a snapshot of what the world looked like yesterday. Okay? And it's not just yesterday. I can actually wind time back and say, I don't want to see yesterday's snapshot. I want to see, well, let's load the whole of the year, okay, all 7 days of it. And so now you're looking at the last 7 days of this imagery of the globe. And you can go back in some of these data sets almost 10 years and look at events that have happened in the past. This data is good for looking at things like hurricanes, typhoons, dust storms, wildfires, and so on and so forth.
Okay, so a little bit of history about what I call the carbonization of the world. How did we get into this mess? This is data on fossil fuel carbon dioxide emissions going back to the 1850s, compiled by the Oak Ridge National Laboratory based on records of fuel. How much fuel is bought, sold, and burned. And what you see here is over a period of about 70 years, from 1890 to 1960, is the rise of the US and Western Europe. Indicated by the height of these cones and their colors, it illustrates where most of the fossil fuel emissions are occurring, right? By 1960, the world that we recognize in the Western world was locked in. The patterns of emissions were largely locked in the US and Western Europe. Now, if we do the same thing in Eastern Asia, we see the same process starting in about 1910 in Japan. And like in the US, it took about 70 years to fully lock into what we expect in China today. By 1980, Japan is about what you see today. And now if we look over at China, the same process started a bit later. 1960, China began its rise as an industrial power, and you'll see the same thing starting here in India. The point of this slide is we're not done yet in the developing world, but we can, if we think that if China and India follow the same path as the US and Japan, it'll take 70 years. And things, despite best efforts, we probably won't settle out to about 2030. If you look at economic models and what these countries are doing, that's probably a pretty good projection. We've probably got about 20 years of this sort of thing ahead of us. And that's one of the threats we face. Mike Gunson already talked about the carbon cycle. I already chided him about updating the numbers. But the point here is there are two effects of human activity on the carbon cycle. One is the greenhouse effect. I'll talk about that in a second. But the other one, which I don't think people have talked about yet, is ocean acidification. If you put CO2 in the atmosphere and it mixes with water in the ocean, you form carbonic acid. This is 8th grade chemistry. If you increase the acidity of the ocean, if you drop the pH, you affect the ability of the foundations of the marine food pyramid, which is the pyramid of life on Earth. That is coral reefs and phytoplankton, all of which build their skeletons on calcium carbonate. You affect the ability of those systems to grow, which puts the entire food cycle at risk. Right? Some people think that this is actually a greater near-term threat than global warming. Real quickly about how this all works and what this means in terms of geoengineering. This is all about balances. I talked about the carbon balance. When I talk about the energy balance, sunlight comes into the Earth. About 2/3 of it reaches the surface of the Earth. The other third is reflected back into space because of clouds, they're shiny, and because of bright surfaces on the Earth, like ice. And then the Earth's surface is heated, and it radiates energy back in the form of heat. Again, most of that goes out into space, but a significant fraction is trapped by the greenhouse effect. Water, carbon dioxide, methane, nitrous oxide, fluorinated gases, these are all chemically, they're warming gases, heat-trapping gases, and they cause the greenhouse effect. So it's this system that we're talking about when I say that people have interventions in mind. So real quickly, what is geoengineering? What are the methods? Well, there's two main branches. One is solar radiation management. There's a bunch of different methods ranging from space to the surface of the Earth that make the Earth shinier. It's about reflecting sunlight, increasing albedo. The other one is carbon dioxide removal. It ranges from planting more trees to increasing the uptake from the ocean to actually sucking CO2 out of the air. And I'm going to talk quickly about 5 methods, right? This just as examples. So the first one is stratospheric aerosols. Mike Gunson mentioned this. Somebody asked about volcanoes. Well, when we have really large volcanoes, not your garden variety volcanoes, but the Mount Pinatubo type volcanic eruption back in 1991 in the Philippines, this dark line that you see in the atmosphere is actually volcanic sulfates in the stratosphere if it stayed lofted for several months compared to before. So scientists actually could measure, but the amount of sunlight was dimmed by a few percent by that eruption. And it lasted for about 18 months. And we measured a significant change, a decrease in the Earth. So, duh, if you reduce the sunlight coming in, you're going to cool the Earth. The problem is these don't last, they're not predictable, and nobody wants to go setting off hydrogen bombs and volcanoes to trigger this, right?
So what we're going to be measuring with this radar, and I don't know if anybody's familiar with the term radar. I mean, it's very similar to what you see in police guns, right? So they send the signal out, it bounces off of a car, it comes back and it tells you something about the car. It tells you how fast it's moving. What we're doing here is we're not measuring how fast something is moving, we're measuring how bright something is. So what's happening is we're looking at the ocean surface, and we're looking at the little waves on the ocean surface. So depending on which direction and how strongly the wind blows over the ocean surface, we get different roughness. So the radar can actually detect that. And from the data that we get, we can actually determine the wind speed and direction. So we're looking at the ocean as opposed to SMAP that is looking at the land. We're looking at global oceans. And we're going to be deducing some information about the winds, the global winds. This information is important for the climate purposes, for the long-term sort of climate measurements and even short-term events like things like hurricanes and things that people talk about more often rather than maybe long-term climate trends, even though that's a hot topic nowadays. So we will be going on a space station. So what Keith was talking about, he was talking about a full spacecraft. He was talking about a full sort of vehicle plus instruments and everything else. We're just one instrument. We're going to get installed on our spacecraft, which is going to be the International Space Station. And we will be just one of the instruments sitting up there and actually looking at the Earth.
When you sit back sometimes and think about the big picture and what this all means, it's a little bit scary. And I think most of us studying these entities don't like to do that because it's a little bit scary. And one thing that's scary to me is that even if we all agreed in this room and outside this room that we ought to do something to stop that, it's going to take a long time to stop it, even if we decide now to do it. So sometimes I'm a little bit resignated as being an observer. My best job is to document the changes that are happening, explain them, and provide the information to people who are going to make changes in policy and government and all that stuff. Right? But I'm also an inhabitant of this planet. So I also have my opinion as a citizen. And that stuff is worrisome. But there's other parts of climate change which I think are even more worrisome than sea level change. For instance, I'm more concerned about the loss of biodiversity than I am about sea level rise. I am more concerned about the effect of changes in precipitation over the globe and how it affects agricultural system than sea level rise. Sea level rise is kind of a big threat, not for me or Julia, but for our kids and grandkids. We're going to be, facing 1 or 2 meters of sea level rise and ask our grandparents, you knew about this, what did you do? All right? You made me buy this house on Newport Beach, and now it's underwater. You made me buy this property here in this island, and now it's underwater. The thing about ice sheet is that they're going to affect us on a long time scale. It's not going to affect us in the next 10 years. But at the same time, this is a big machinery. Right? This is a huge process that started. It's on a path. In my opinion, what's going to happen in the next 100 years in Greenland and Antarctica is already written in stone. We can't quite change that. But we can probably change what's going to happen beyond that. And the world doesn't end in 2100. So that matters too.
Hi, I'm Carol Barbee. I'm with the WGA. I'm a writer-producer. This trip to JPL has been amazing. It's been a dream to come here and to be able to hear these amazing client scientists talk to us and give us the real data and their opinions about what needs to happen and what is happening. It's been very interesting and inspiring and makes me want to not only write about these issues, but get involved in making sure we do the right thing.
My name is Wally Wolodarsky. I'm a long-standing member of the WGA and currently working on a couple features. And I actually really enjoyed the tour because it feeds right into a script I'm working on, which is a comedy, which doesn't necessarily seem like you might address some of these dire issues in comedy, but I'm going to give it a shot with my writing partner, who's my wife, Maya Forbes. And so I found it very useful, very informative. I may do a little crying in my pillow tonight when I reflect on what I heard, but other than that, I thought it was very worthwhile.
Hi, I'm Andy Cobb. I'm a comic living in Los Angeles, and I had a great day today. This has been fantastic. I thought the information was great, but it was also presented in a compelling way. We get to do cool stuff, like we got to be in mission control, where they control and get information from all the satellites circling the globe right now. But it was great, it was informative, and I think it sparked a lot of creative projects and some of the stuff we're working on, the documentary and these other projects. It's a lot of great information. So thank you for having us. It's been delightful.